Harvard. She's going to talk to us about a new perspective on high-dimensional problems.
Thanks so much to the organizers for the invitation to speak here, and thanks to the amazing talks and tutorials the last few days. I've certainly learned a lot. So I'm going to talk about causal inference. It's a topic that has not been touched upon that much in this workshop yet, and it doesn't seem directly related to deep learning theory. But it is, first, this is an area that has piqued the interests of researchers across varied communities: statistics, econometrics, machine learning, computer science, and so on. And second, it's also an area which actually provides us interesting questions of statistical inference with which machine learning can interact quite a bit. And you'll see at the end of my talk what I mean exactly by that. So this is joint work with three wonderful collaborators. Guanhao Jiang, he's currently a second-year graduate, finishing second year, rising third year, grad student in Harvard Stats, and it's been really amazing working with him. He has infinite amount of energy. So I think people who work on causal inference would probably agree that it's generally a very hard problem, and causal inference in high dimensions is okay, that's even harder. But at some point we were stuck with sort of pages and pages of math, and it was really like Guanhao's persistence that saw us through. So really kudos to him for this collaboration experience. Rajesh Mukherjee, he's currently a faculty assistant professor in the Harvard School of Public Health and a great collaborator, and Shivabrata, who is in the audience, and many of you know him. He's also in Harvard Stats. Okay, so the problem for today's talk is causal inference from observational studies. I will not assume much background on causal inference from the audience, so I'll try to give a short tutorial at the end to make sure everybody's following along. But this is also my first paper on causal inference, so there are errors in the tutorial. I'm not the person from whom you should be getting the tutorial, so that's just FYI. And our main goal, our end goal, is to sort of understand these problems in settings which we can call high dimensional, without strong structural assumptions on underlying signals. Specifically, we're trying to move away from sparsity assumptions. So your signals could be sparse or dense, you just don't know. And so we're trying to build theory and methods in these settings, and that's the end goal. And in this talk, we'll sort of take some of the first steps towards that goal. Okay, so there is one main result in this talk. It's a new central limit theorem. So once I present that, you'll see it's some nice estimator is written consistent as a statically normal. It's all about characterizing the variance. So you can go to sleep after that. That's like the main result. And I will say some insights into our proof techniques and time permitting, but that will merge nicely with some of the material Ahmed was covering in his tutorial this morning, because we do use quite some insights from the fields of statistical physics, high dimensional probability, and so on. All right, and as I promised, there'll be something on opportunities and implications for machine learning. Okay, so what is the problem? We are in a slightly different setting here than the supervised learning settings you've been seeing through large parts of this workshop. So now we have NIID samples for this talk, but I have three kinds of variables. So the yi's are my outcome or response variable, the xi's are my covariates in some p dimension, but I have another set of variables. These are the treatment variables, and for this talk, they are going to be binary. You could talk about continuous treatments, but we are going to talk about binary treatments for this talk. And the main question in causal inference is, can we estimate the effect of the treatment on the outcome? So the treatment could be whether you assigned chemotherapy or not to somebody, and you want to understand, is that effective? Okay, but this is a humongously challenging problem. Why? Because I'm talking about data I've observed, and I had no control on the design of that experiment. So the issue here is, for every unit or individual I, you only observe the outcome corresponding to the assigned treatment. So for any given individual, you never get to see what would have happened if the other treatment would have been assigned. And among many challenges in causal inference, that's often referred to as a fundamental problem. And so to navigate this problem, what do you need to do? We need frameworks for talking about these things. And there are many frameworks that have been proposed over the years. The framework I'm going to work with today is the framework of potential outcomes, which is also alternatively known as the Neyman-Rubin causal model. And what does this causal model tell us? It basically says that let's denote YIT to be the outcome we would observe if treatment T were assigned to individual I, and I don't get to see both of these in my data. But once you define these quantities, you can talk about how to estimate the effect of the treatment on the outcome. And how you estimate that is by introducing various target parameters of interest, which have some causal interpretations. So the simplest of this is the average treatment effect, which is simply expectation of the difference of these potential outcomes. One step up in some sense is the conditional average treatment effect, which is this expectation, but you're now looking conditionally strata by strata, depending on the covariate values. And so there can be many other such causal effect estimands. That's what we'll call these. And this talk will be about the simplest and perhaps the most canonical one of these. Okay, so we'll talk about the average treatment. Yeah.
It's T01, right?
Which one, sorry? A?
T01, right?
T is 0 or 1, right? So for this talk, I'm keeping T to be 0 or 1. Yeah. Okay, now what's the problem? As I said, you never get to observe both outcomes for any individual. So you actually expect this to be an ill-posed problem. So I cannot identify this parameter from my observational data without further assumptions. So there is this entire sub area of causal inference broadly that tries to figure out what is the structure I need on my observed data distribution so these causal effect estimates can be identifiable. So I'm here laying out sort of 3 standard assumptions. You can find this in sort of causal inference textbooks. They have different names depending on the branch of causal inference you're working with. And this talk will not be about identification. So, this is all causal identification. It's a huge, huge literature. And people are stress testing these assumptions, trying to come up with better assumptions and procedures for testing this and so on. So this is causal identification. And what it says is that under some standard assumptions, quantities like the ATE can be identified from the data. And what that means is the following, that you can write your ATE, which on the left side was, its functions of at least one of them is unobservable for each individual, right? You can express your ATE as a function of the observed data distribution. So the right-hand side is based on conditional distributions and marginal distributions of your observed data, right? So if you can have such an identification equation, then your goal now, we are in inference land where you try to estimate this quantity given the data you've observed. Okay, so our goal today is to not think about when this inequality is true, but try to estimate this quantity. Okay, so that's what you need for identifying this parameter. And then, so now we can talk about ATE estimation. And that's a very, very well-studied problem in the literature. And there has been seminal works in this context, right? But if I were to sort of quickly summarize the flavor of these works, what I would need to do is introduce 2 nuisance functions that show up. And what's a nuisance function? It's something that's not your actual object of interest, but it shows up in the process of estimating the ATE. And the first nuisance function is the conditional distribution or the conditional mean of your treatment variable given the covariates, and that's called the propensity score. And the second nuisance function is the conditional expectation of your outcome variable given the treatments and the covariates. And because the treatments are binary here, I can simply look at these 2 conditional distributions individually. So these are known as our outcome regressions. So what sort of happened in this literature is based on which one you're modeling, different approaches were proposed. Perhaps one of the most classical ones or inverse probability weighting goes back to classical literature and sample surveys and so on. And that really tries to model the propensity score as well. Now you can flip around that view and instead try to model the outcome regression as well. That gives you the class of estimators known as G computation broadly. And then of course, you have 2 nuisance functions. You can hope to talk about how can I smartly model both of them or borrow best of both worlds. And that falls broadly under the category of what are known as augmented inverse probability weighting estimators, targeted MLE, and so on. Okay, in some sense, this third thread is better in the sense that it tries to combine the best of the both worlds. So today's talk is about this augmented IPW. A lot of you might know this estimator under the name of double robustness or doubly robust estimator. I use this term because we will be in slightly different regime than existing literature where it's unclear if it still stays doubly robust or not. So I used its like original name from when the thing was introduced in the literature instead of using the term doubly robust. So this estimator will study. And so and this is very commonly used because it has nice properties. I'll show you that. But just so we're all on the same page, let me first introduce this estimator formally. So to introduce this AIPW, that's a natural acronym. So what it does is it computes estimates for these nuisance functions and then uses a plug-in principle. Seems natural. So let's denote these to be our estimated nuisance functions. You can have an estimator for each sample because you have a different xi for each of them, right? And then the AIPW is simply difference of two terms. Okay, that's just math equation, not really giving us much insights, right? So this is my first term, this is my second term. You can see I have labeled them by the treatment values. So that should say that this first part is corresponding to the treatment arm, and the second part is corresponding to the control arm. And the best way to see that is AI is 0 or 1, right? So if AI equals 1, this term actually survives. So you see the contribution here. Whereas if AI equals 1, this term vanishes. So if AI equals 0, then this term survives. So this is what's happening along each terms. But the important thing here is there are two parts to this estimator, right? The first part is your classical inverse probability weighting. It is really trying to model the propensity scores and doing inverse probability weighting. And it's using nothing about the outcome regressions. Okay. And this is the second part. And now we see the outcome regression estimators showing up. And there's a rescaling factor, which is actually very carefully designed. The rescaling factor involves the propensity score estimates. Okay. And this combines best of both worlds in a sense that when you analyze this estimator, you look at its deviations around the true ATE, then in some sense, the error terms that show up as products of two error terms. One part comes from the propensity scores, one part comes from the outcome regression. So if you have products of two errors, then if you model one of them really well and your error is really low, you can pay less price for the other one. So if something is really, really small, you can still multiply with something a relatively large thing so that the overall thing is really small. So that's the idea. That's why you have sort of two parts to this. Okay, so that's classical AIPW for you. And I summed over all the observed samples. Okay, cool. Now, why is this estimator so popular? It's popular because it has this fascinating double robustness property. It remains consistent. I'm just talking about very classical work here under fixed dimensions, large sample asymptotics, even when one of the models is misspecified. And it happens precisely for this reason, that if you look at these deviations, you get product of two terms. So, you have some room to play with. Okay, so that's classical causal inference in 10 minutes for the background I'll need for this talk. So now we are jumping, yeah.
What's misspecified?
Ah, right. Okay, thank you for asking me that. So what I did so far here, I just wrote this as conditional expectations, right? And I did not assume any model on any of them. But in practice, you could maybe model these by parametric models, or people also do non-parametric models, right? So this AIPW has this nice property that, if you have a model for this, that's your propensity score model. If you have models for this, that's your outcome regression models. And so AIPW has this nice double robustness property that even when one of your assumed models is wrong for one of the nuisance parameters, the estimator still remains consistent for the ATE. So it allows natural misspecifications, and that's why the form of the estimator is really important. So you can be completely misspecified in one of the nuisance models and your eventual estimator is still consistent for it. Okay, and so I said double robustness, and the classical definition is like this, but actually this estimator does more. It stays root inconsistent asymptotically normal also when things are misspecified. One of them is misspecified, so all of this kind of understood now. Okay, so fast forward to the recent few years, there has sort of been an explosion in understanding causal inference in the presence of high dimensional covariates or confounders, whichever way you might call it. And of course, the natural reason is because we have a lot of high dimensional data everywhere these days. I don't need to motivate high dimensional data for this audience. But also there is another reason that is often cited, that is having an unmeasured confounder that affects both your treatment and outcome invalidates your causal statements. So if you had access to lots of variables, you would basically like to include all of them. And that might be your one good hope to mitigate the unmeasured confounding issue. So, okay. But basically point is, for a lot of reasons, we need to have valid theory and methods that allows us to do causal inference in the presence of high dimensional covariates, and there have been lots of works along these lines. And broadly, these works try to push the frontier on double robustness. So there's lines of work which are known as rate double robust, and there are lines of work which are known as model double robust. And what they do is they try to allow different forms of misspecifications and sort of push the frontier on what you can say, even when you're in very high dimensional settings. And when I say high dimensional here, most of these are sort of, the number of variables is really, really large. So ultra high dimensional, much larger than number of samples. And a common theme in this literature is you can have number of variables to be really, really large, but whether you have well-specified or misspecified settings, at least one of your nuisance models has to be highly sparse. Okay, and that's a common theme. And that's there for reasons that you really need it in those regimes. So, okay, for the theoretical analysis and so on and so forth. So that's a common theme that across this literature, at least one of your nuisance models needs to have highly sparse structures for the theory and methods to work out. And this is sort of where we come in to motivate what we're trying to do and why we're trying to do that. I'm going to show you this simulation, and to some of you in the audience, this might be familiar if you're familiar with the high dimensional regression literature. So here, what we are doing is the following. I have number of samples is 10,000, number of features is 700, so it's moderate dimensional. It's not really high dimensional in that sense. And we're just plotting a version of the AIPW and what it is that we are exactly plotting. So we are taking the AIPW estimator, empirically calculating its standard deviations and doing many replicates of this and getting histogram of those objects. And that's the blue histogram on the right. Now, if I go back to the existing literature, whether classical fixed dimensional asymptotics or the sparse ultra high dimensional literature in such a setting, this is the red line. And what do I mean by such a setting? So there is a lot more that's happening in this setting. I have sort of IID Gaussian designs. I could change the designs to be sub-Gaussian. That part matters less. But the crucial thing is I have used a linear model for my outcome regression. I have used a logistic model for my propensity scores. And the underlying signals are IID Gaussian. Okay, so for this simulation, that means all of the coordinates are non-zero. And the fact that all of them are non-zero is less important. Even if a positive fraction of them were non-zero, we would see something similar. But there is something about we don't have spiked non-zeros, which are really large and everything else is zero. That's not the structure. So what do we see here? We see that the true variability of the estimator is much higher than what the existing results tell us. And this kind of variance inflation by now is very well understood in the context of high dimensional regression. When you just have a vanilla regression problem, you're trying to infer coefficients there, something similar happens. That's more or less well understood by now. And in the causal inference context, formally, I mean, although you expect such variance inflation, and it was alluded to in the econ literature for several years now, it was formally pointed out in this recent really beautiful paper by Steve Yadlowski. So what does this tell us? It tells us a few things. First, the existing ultra high dimensional literature does not capture these regimes, and those results can actually fail when you move away from some of the sparsity assumptions. And two, you don't even need to go very high dimensional to see such phenomena. Okay? So our goal is to try to explain this plot through this talk, and nothing comes for free. So instead of assumptions on the signal structure, we will have strong assumptions on the covariate distributions, and then we'll sort of discuss how much of those can be relaxed and so on and so forth. Okay, so I more or less motivated this. So what's our goal? We want to analyze a commonly used version of the AIPW in a regime that we can still say this is arguably high dimensional in the sense that you see pure high dimensional effects in that regime without assuming any sparsity type assumptions on the underlying nuisance parameters, whereas the nuisance parameters are high dimensional. All right, so there are a few parts to this question. So the first part to this question is understanding AIPW in some regime like this. And the moment you go to high dimensional regimes, the AIPW that I introduced before kind of doesn't work directly. Instead, there are versions of that estimator that people have come up with, which they actually work with, because the original AIPW where you're computing the estimator with all the n samples, it is actually very hard to analyze. So what I'll do next is I'll first introduce the versions of that estimator that people usually look at in high dimensions, and then sort of segue into our formal setting and then our results. Okay, so what are the versions of AIPW? Yeah.
So when we are saying high dimensional here, like, so I'm guessing, are you thinking of P still smaller than N, but you want like the previous results to be more capture better what happened?
Right. So I'll hold off on that question because for our main result, that is sort of the regime we'll be in, but there are lots of layers to that question. So I'll sort of slowly segue into what I mean by that. So maybe I'll hold off on answering that right now, and you should find the answer. So yeah, any other questions before? Okay, so first thing that happens is you have a large number of covariates. If all your nuisances and ATS, everything's calculated from your full data, things become intractable, and there are also other issues that happen. So the standard thing that people do is sample splitting and then cross-fitting. So let me explain. One thing you could do to analyze these estimators better in high dimensions is you split the sample into, let's say, 3 parts. You had 2 kinds of nuisances that you need to estimate. Estimate your nuisances from 2 of the folds, and then you estimate your final AIPW from a separate fold. Okay, so you had 3 folds. So then you can switch the role of the folds, like we often do. That gives you 3 factorial estimators, and then you can average them. So this final step where you're averaging all of this, that is called cross-fitting. And there are other versions, right? So for instance, I can split into two folds, calculate all my nuisances from 1 fold, the AIPW from the other, get 2, average. Okay, so that's version 2. And something really nice that used to happen in the earlier literature, even if when you're ultra high dimensional, if you have nice sparsity in at least one of your nuisances is, so let's focus here. Before the averaging, I have 3 factorial estimators. And on the Rutan scale, what happens in the earlier literature is the covariances between these estimators becomes asymptotically negligible. So what is effectively happening is you're sample splitting to keep things tractable, but then when you average, you gain back the lost efficiency. And that's really nice. And that has sort of, that's why you should cross-fit in reality, right? So this is sort of what happens in prior works. For our talk today, we will focus on this version. And one thing that we will see is we don't have this nice vanishing cross covariances anymore, but I'll make that precise. So this is where we'll focus, just so we are all on the same page. I'm sorry for repeating, but sometimes it's good to repeat to make sure that we all know what estimator we're looking at. We're splitting into 3 parts, propensity scores from 1 part, outcome regressions from the other part, and the final estimator is from the 3rd part. And that gives me 3 factorial estimators. If I switch the roles of the 3 folds, we average this, and that's my final object. So what do we call this? I mean, we don't need to name this, but it's helpful for the talk. So it's a 3 split into 3 parts, cross-fit 3 split AIPW. It's not known by this name in the literature. It's just AIPW is a general estimator. You can do it whichever way you sample split. So, but just so we know what we're talking about. Cool. So now maybe I'm slowly getting into things that starts addressing Ladri's question. What do we want to do? We want to understand this estimator going away from sparsity assumptions, right? So what are the main hurdles? First main hurdle is, okay, so we have these 3 factorial estimators before averaging, and maybe what we want to do is let's characterize their asymptotic distributions pre-crossfit. But okay, that's not enough because we're cross-fitting, so we need to understand joint dependencies eventually. But even when we want to do this, if we don't want to assume much structure on the signals, up to P signals are allowed, right? All of them could be non-zero. If you want to have sort of a motivating example for this setting, such settings are known as many instruments or many regressors in the econometrics literature. And there are surveys written on these kinds of settings. And so what happens is the moment I allow this, it's sort of the moment P is going to diverge higher than small o of n, you would start observing high dimensional effects in the sense that on the scale of these orders. So even if the ratio is, even if P is less than n in some sense, but it's diverging at a rate higher than this, you should already observe high dimensional effects. So this is starting to get at what I'm calling high dimensional in this scheme of things. Okay, and as I said, just this asymptotic distribution is not enough. We need to track the joint distributions. And so suppose magically I know they're jointly Gaussian, then what I need to track are the variances and the covariances between these. All right, so we need theoretical tools that allow us to do this, and that applies for a broad set of dense, sparse signals alike in these kinds of high dimensional regimes. There's a whole or more than one area that gives us such tools. They are, they come from statistical physics and parts of probability. And so at the end, hopefully we'll go back to some things that Ahmed was talking about today. And just to highlight, this is not very hard. What will be hard is understanding the covariances between all of these estimators when I don't have much signal structure. Cool. So now I get into my formal setting. And this is where, like we were told to be critical of our own work, right? This is where there's a lot of things to critique because we're trying to get at really precise answers, going away from signal structure, and that comes at a cost. So the price to pay, at least for this work, which also is one of the first central limit theorems in this regime. So hopefully we can relax some of the prices, but right now not yet. So the price to pay is, okay, we have well-specified models for my propensity score. So these were, the treatments. So they're Bernoulli with some link function, some xi transpose beta. We did it with the logistic link, but anything else that's like that should also work. And then we have a linear model for the outcome regressions. And my formal high dimensional setting is this proportional scaling regime, where the ratio between number of features and samples is going to some positive constant. For our theorems, we will need to restrict the ranges where this constant can lie. Okay. This is the strongest assumption. For now, I only have simulations to show you that this is not the only regime where our results work, but there is a lot of universality result that does need to be proved in this area to relax this. Okay, so we don't have sparsity structure on the signals, but we do need something, because if you don't assume anything, your signal to noise ratio can go to 0 or explode, and you would not hope to do, in one case the thing should become trivial, in the other case it should become too hard. So what I'm writing here, it looks in the form of these, if I define an empirical distribution on these parameters that gives mass, let's say 1/p to each of these coordinates, then this is really the moments, the second moments of that empirical distribution. But it looks odd why this thing comes up. A better way to probably visualize this is if I take the variance of my log odds, that's basically, so that's just variance of, let's say, xi transpose beta in this first model. And this is a rescaling of that because I have normal zero identity over n. So what I'm really doing is I'm trying to hold the signal to noise ratios to be finite in the limit. And this part is just saying that my two regression models, you can't be like wildly different from each other in some sense. So these are, you should think of these as SNR, controlling the SNR, having moderate SNR problems, and I don't want these to be infinite. Yeah. Okay. I want to comment a bit about this regime. You can call it whatever you want. You can call it proportional asymptotics, proportional scaling, but there have been many different areas that have been looking at this regime. On the stat side, it started with Johnston and Liu, or maybe even earlier. We have all of the random matrix theory stuff, and more recently, people have been looking at this regime in the context of other problems where you use tools from stat physics and probability theory and so on. There's a whole econ literature which does this, and that is the many instruments and many regressors line of works. And in machine learning, we know of such scaling limits, right? Not all of this are in this exact setting, but even when you're taking certain scaling limits of like how many neurons you have and how things are growing, you work with such scaling limits, and you see a lot of phenomena because of nice scaling limits. So I didn't include any references here because there are a lot, and these are really sort of the areas from where a lot of the tools, I at least use a lot of the tools from. So if you're interested in the original references here, I'm happy to speak after the talk, but this has much older roots. I mean, I mean, George Percy got the Nobel Prize last year, and he's the creator of the cavity method that, one of the co-creators and stuff that Amit talked about. Okay, so this is our main result. Under sort of the assumptions that I laid out, if you estimate nuisances using things we can nicely track, I'll come back to this. Then the AIPW I was interested in is, as I said, we have one CLT, it's a root inconsistent, asymptotically normal. So what's going on? Why was it hard to prove the CLT? Because we characterize the variance pretty explicitly. And one of the things you can do once you characterize this variance is that clearly it's much higher than the classical variance or the previous ultra high dimensional literature variance. So this explains the variance inflation plot that I was talking about. The other thing that happens is, I'm sorry, it's written in these equation forms, but this part actually has a nice interpretation in that if you look at your xi transpose betas along the treatment arm and the control arm and take difference of the norms of those, or like just the absolute values, in the limit, that's what you get. And you actually expected to see that difference somewhere. Okay, so that's sort of the main result. Let's do some stress testing or simulations. First, it's really simulations in our setting. So what are we doing here? I'm plotting sample quantiles versus theoretical quantiles of the AIPW estimator. And so the darker blue points correspond to our formula just from the previous slide. And this is the classical formula, which also is the same as the sparse ultra high dimensional formula. So the variance is different for these two plots. And you can see that in these sorts of settings, it's a similar setting as my variance inflation plot. That was our home ground. So naturally we do better. That's not a surprise. Just saying, what is this plot? So the AIPW has these propensity scores in the denominators. And so if I use, let's say, logistic models, I'll get the sigmoid here. So if that becomes close to 0 or 1, things blow up. So what people do in practice is they just trim this object, so that they're away from 0 or 1. So this is just a bit more, so on the tails, it's a bit better. Okay, so any questions so far? So the plot I want to spend some time on is this one, actually. So what am I doing here? Remember, we were looking at this AIPW, which had sort of 3 factorial estimators I was averaging. Here, I'm taking one of those estimators and looking at its empirical standard deviation scaled by 1 over square root 6. Okay. Because I have 6 of these, I scale that by 1 over square root 6. So that is this histogram. But now I look at the CrossFit AIPW, which was averaging all these estimators, and that the empirical standard deviation for that is here. So this difference is not observed in the broad literature. So cross-fitting, okay, this is a setting where the blue histogram moves to the left. So what does that suggest? That suggests that cross-fitting buys you a lot, because if there are no covariance terms, then these would have been the same, essentially. Yeah, so maybe I can write for this particular plot, okay? So my AIPW CrossFit is I have sum over I in some set. There are, 3 factorial many Tahoe at AIPW1, and I have these things, or just I, right? So there are 3 factorial things. And now I'm claiming that this plot shows, at least in this setting, that the covariance between these is non-negligible. So the right-hand side is just my standard deviation of one of these. Marginally, they all have the same standard deviation. Okay, scaled. And the left-hand side is this object. And so this is a phenomenon that surprised us because, of course, lots of benefits of cross-fitting have been talked about in the literature before. And the main argument has been, oh, if you sample split then cross-fit, you recover back the lost efficiency. But here it seems you actually gain more. So we were very excited about this initially. And then, so now I don't want to claim much because in some settings we are starting to see this might also go a bit to the right. So what happens is how you estimate your nuisances really matters. But the main phenomenon happening here is that your cross covariances are no longer non-zero at the root n scale. whereas this is not something you would observe before. So it's very important how you do your nuisance estimation. Okay. Okay, so the other thing, we were interested to see this, although we expected this, and I think you would expect this. That is, when so we can use ridge regression for estimating the propensity scores. If we use that and we plot as a function of the tuning parameter, the standard deviation of our estimator, then this is the plot you see. And so if you try to obtain the lambda by optimizing for the prediction error, you would not recover this. So I don't think that as a phenomenon should be surprising. And this we are doing with leave one out cross validation, which for the prediction error should be consistent. So the plot shouldn't be surprising, but what this says is we actually need better ways to tune our tuning parameters that are explicitly optimized for the inference properties of the estimator. So for instance, we need to identify this lambda if we were to use ridge, lasso, whatever. And for that, we actually need a good estimate for the downstream variance that shows up in our CLT. So that's something we're thinking about now. We don't yet have that, but there's something to lay out that if we just naively optimize for prediction error, we would be far from the optimal lambda. So these are some of the immediate upshots, and you can stress test assumptions in simulations, right? And these are basic simulations to see what happens if my covariates were not Gaussian, but let's say they are sub-Gaussian. So we did it for many settings. We kind of expect to see the same thing if you have sub-Gaussian tails, and there are universality results in the area that allude such things would happen. So this is just for a uniform. You see a similar plot, and this is for a discrete distribution when your covariate values are supported on 0, 1, and 2. But that's not a proof. Okay, so there is a long way to go in terms of how much we can relax the assumptions on the covariate distributions. Okay, so how am I doing on time? Okay, sure. Okay, so now what I want to talk about a bit is about the proof techniques, because one thing that happened was, slightly to my surprise, I've worked on this professional asymptotics area quite a bit before, but one thing that happened here was we needed a few different proof techniques, and then we needed to put them together as sort of pieces of a big jigsaw puzzle, and that was a bit of a surprise. So one of the techniques we use a lot is this leave one out technique, which is alternatively known as cavity method in statistical physics. It has really old roots in that literature, and if you're interested to study this in the context of, let's say, statistics regression problems, then a really nice short reference is this paper by El-Karoui et al. In the Proceedings of the National Academy of Sciences. So there they actually did it for linear models, and the derivation is really short. And it's nice to read in the sense that usually cavity method papers are pretty long. But because this was 6 pages, I learned the stuff from there. So I strongly recommend if you have to learn this, this is actually a very good reference. If you're interested in like GLMs and stuff, then you can look at some of my earlier works. And then there are also more recent works on spectral methods and stuff by Chen et al. It's a really nice survey. Okay, so that's one of the techniques. The other technique we used is this whole sort of zoo of things known as approximate message passing theory, and Ahmed presented that quite a bit for one of the models. And what this does is, okay, so what does leave one out do? Its main goal is to help you decorrelate dependencies in various terms. At least for my purposes, that's what it does. And what does AMP do? For my purposes, it has other uses, but I usually use it as a proof technique. So it basically helps track properties of estimators in models where you don't have closed forms for your estimator. So whenever you don't have closed forms, things become hard to track. At least in the proportional regime, you can't do random matrix theory stuff. With some recent developments, maybe you can in some cases, but in a lot of cases you can't, and that's where this sort of tool comes in. And then we actually also needed something known as deterministic equivalence from the random matrix theory literature, and this helps track quadratic forms of random matrices by connecting to more tractable deterministic matrices. So what I want to do in the next few minutes is try to give a crash course on these two and sort of show a bit how these show up and why these are important for understanding certain models and statistics. Okay, so this is a very quick peek into leave one out in our setting. Now, to describe this, I have to remind you that what was our CrossFit AIPW like? The AIPW had many terms, but without crossfitting, it had something like AIYI by propensity score estimates. So if I assume a logistic model, let's say, my estimates look like the sigmoid applied to Xi transpose, let's say some beta hat, and our theorem was for the ridge regression. Okay, so these terms show up. There are many other terms, but the important thing is that for the CrossFit estimator, I'll have these terms when my eyes, let's say I is in the first split, and the corresponding beta hat could be from any of the other splits. So that's nice because those are independent, right? But in the CrossFit estimator, when I'm averaging 3 factorial quantities, somewhere I have all the i's from S sub A, and somewhere else in the estimator, I have the beta hat from that same fold. So there are lots of dependencies. And so what the leave one out allows you to do is you get something like, Xi transpose beta hat. Let's say this is from S sub C and this is from S sub A. And then somewhere else I have from S sub A, and J could be, let's say, let's just switch. So what it allows you to do, it starts helping you to decouple things. So what I could do is, let's say for simplicity, this is from S sub B. This is for simplicity, but we'll get more complicated terms too. So my dependency here is arising because of the Xi from S sub A and this from S sub A. But the nice thing is you can calculate the same estimator by leaving out the ith observation, right? And that gives me except you incur an error because of this approximation. So you have to track this error. So this slide is a I don't know, it's a not so good attempt at trying to say exact this step. That is, what we do is we connect your beta hat SA to the leave one out quantity. One question you can ask is, how do I connect them? The way you connect them is this satisfies some, let's say this is my regularized likelihood function. So this is solution to some, this has some, or solve some first order stationary conditions. And then I can leave an observation out. I get something like this. So these arise as solutions to first order stationary conditions. You basically just write them out and do nice algebra, but somebody has to teach you, like some nice paper has to teach you how to do the algebra for the first time. Okay, so that algebra gives you a relation like this, where this object does not depend on these observations. Okay, cool. That's nice because I know a lot of stuff about these kind of quantities. And even we observe quantities where I have, let's say, the Xi and a beta hat, and I drop this out. So I know that these kinds of quantities, these are independent. So I basically have these to be, if I have Gaussian covariates, I have Gaussian with some norm squared, roughly conditional on this object, right? And then if you can show that this norm object actually concentrates, you can track this quite well. So that's how the leave one out is helpful. It's really helping to decorrelate dependencies, as I said. Now, suppose I have to track these kinds of norms. Let's say the underlying model was logistic regression or something that doesn't give me closed forms. Okay. The same leave one out can help you track that. That proof becomes many more pages long. So I don't know if we want to do that. But there is this whole other set of tools that helps you track any low dimensional functional of this form. whenever estimators don't have closed forms, and that's where your approximate best pricing comes. Yeah. Can you say a bit louder? Sorry.
Do you need it for a
Okay, that's a regression. So for this heuristic derivation, I actually don't need any Gaussianity. It is really like write out your optimization equations, and you get this relationship. To make things formal, you need actually up to sub-Gaussian tails. But we start needing Gaussianity when we go to the what's the actual distribution of the estimator and stuff like this. So we need Gaussianity downstream in proving the CLT. Well, in some sense, we need Gaussianity to track these things, but okay, we need Gaussianity in many other places. But the concept of leave one out is really, if your system satisfies certain stability conditions, then at least leave an observation out is okay. I haven't told you what's the problem. The problem is we don't have one leave one out step, and that's how causal inference is different from regression problems. We have many of these steps. So these errors actually accumulate downstream. So that is where sort of our contribution was in this work. But if I were to just explain leave one out, I can just explain it writing out these KKT conditions. Other questions? Okay, so I'm going to quickly gloss over the main steps of AMP. In this case, it's a big sort of machinery, so we are not going to cover it in like a few minutes. But what does this machinery allow us to do? What it does is basically, okay, so I said the MLE, but it can be something else that satisfies, let's say, a first order KKT condition. Doesn't have a closed form, hard to track in high dimensions, so we want to replace it by a tractable surrogate. So what is it that you do? The first step is you need to introduce a suitable iterative algorithm. What does suitable mean? Suitable has two stages to it. One, the algorithm needs to be such that we can analyze the asymptotic behavior of the algorithm iterates, because otherwise, why am I introducing my algorithm, right? Like I can't study this estimator, and if I then introduce an algorithm where I can't study the iterates, that's not helpful. So I went from one intractable problem to another, right? So it's a really nice algorithmic proof technique for this work where the algorithm iterates are, their behavior can be tracked, and that's tracked using a formalism that has been developed in the literature known as state evolution in a series of beautiful papers by Donahoe, Maliki, Montanari, then Bayati and Montanari, and in more general models, Javan, Mardan, Montanari. But that's one part of the suitable. The other part is your algorithm iterates need to converge to your estimator of interest in some appropriate sense. Because I want to track this object, right? So I went here, but then I need to come back here. And so what happens is for this first step is always the pain, in the sense that you have to understand what algorithm you should be looking at for your problem. So you need to come up with it. This step, you can rely on existing literature. Once you have AMP algorithms, you can usually cast it in one of these forms and calculate, track this behavior. But this last step is always problem specific, and problems need a lot of structure to do this last step. But what it gives you as an upshot is you can track. So what you can track, let me just show here. You can track norms very easily. And if you can transfer all information of the iterates to your estimator, you can track norms of your estimators, and that's what we needed. Okay, so why is this hard? None of this is actually new, because AMP for all these things was done by other people and myself in the past. It's hard for this precise reason, and I alluded to it in answer to Konstantin's question. That is, causal inference really uncovers novel challenges, and that's because when you look at these estimators, you have, among many other quantities, all of these. So I can be in SA or SB or SC, one of the three splits, and then K is equal to one of the others. And you need to look at all of this simultaneously, right? So leave one out helps decorrelate pairwise dependencies. It's always an equation like this. And each time you use it, you pay a price. So if I use this leave one out relationship n times, and I don't have errors that are at the right order, these errors are going to accumulate. They can accumulate pretty bad. So we actually need to track many of these dependencies simultaneously, and their terms accumulate, and that requires very careful analysis. So if I had to sort of summarize in a nutshell, why we had sort of one result, but the proof took like 100 pages. It's because, they start accumulating, and we didn't realize it when we started the problem that the cross-fitting is just going to be so sort of difficult, but that's the price you pay if you want very precise answers. Okay, so what are the steps where one could interact with machine learning? We were doing pretty naive nuisance estimators, and note I restricted to MLE for the outcome regression always. And what's actually done in practice following this double DeBas machine learning work and several others is you use pretty fancy modern machine learning based methods for nuisance estimation. And so we do not understand yet how, what we proved and results like this, how that interacts with if you use more fancy nuisance estimators. I mean, there are obvious roadblocks in our proof, but there's also a lot that has been understood under such scaling limits on the machine learning side in the last few years. So maybe there is some hope that these can be, meshed together nicely. Okay, so quick summary. I showed you a CLT in an arguably high dimensional setting for the CrossFit AIPW estimator. This was our goal, moving away from these assumptions. It comes at a price. We quantified the precise variance inflation. And something to note is if you assume sparsity now within our stuff, you'll go back to the variance that was before. So in some sense, you recovered that in the limit, but we don't have a formal proof of that. If you simulate in very sparse settings, using our formula, you'll get back the classical formula. Okay, and we see these non-trivial CrossFit covariances or covariance between these 3 factorial estimators, which is certainly a new high dimensional phenomenon, which wasn't really observed before. And so why do we care about CLTs? Because they give us at least asymptotically valid confidence intervals if you can estimate the variance. And that's sort of a big question going forward. And there are, of course, 2 easy to see. I mean, okay, I don't know if elephants in the room are easy to see, but there are 2 elephants in the room. And of course, like, how do we relax these assumptions and how do we go to more general nuisance estimators? And of course, then what happens to other causal effect estimators? Okay, so I'll finish with that. Thanks so much for your attention.
We have time for 1 or 2 questions.
So when you talk about double machine learning, is it using different estimators to estimate those nuisance parameters and getting CLTs using sort of maybe more involved MLEs? Was that?
Right. So the double. So what I didn't say was this AIPW is part of this double machine learning based estimators. And so what changes there is really how you estimate the nuisances, but the AIPW formula is the same. But they are able to go to more fancy nuisance estimators, assuming structure on the signal. So there's a trade-off between what you're willing to assume. But in that setting, you can use more fancy estimators, and as long as you have some assumptions. So they actually want to estimate the nuisances sort of consistently, and then do a plugin. But something that's important is in our regime, you can't really have consistent nuisance estimators. You can't estimate the full p-dimensional vector consistently. But what's important is you can still get AT estimates that are consistent because the AT is a low dimensional parameter. So there is a fundamental difference between the two regimes. Yeah.
The plot you showed with the cross-fitting having lower variance than the Monte Carlo sampling. Basically, right? It would be as if you had sampled the same number of things independently and averaged them.
So they are both Monte Carlo.
Right.
So they are both Monte Carlo. Just I'm plotting a different estimator. So one of them was one of the 3 factorial estimators, just its variability scaled by
So the difference between the 2 is that one, each summand is independent and the other is not.
Yeah.
So I'm trying to figure out why I should expect. That's not true.
No, sorry. So I was trying to say through that is none of the summonds are not independent. So let me go back. Okay, sorry. Let me go back. So if I go to either fixed dimensional settings or the sparse ultra high dimensional,
Right.
then all the summonds will be a remittance scale independent at some time. And then if I take one of them, let's say this is my summand 1, and let's say I take its standard deviation, right? So what do I get? I have basically 1 over root 6 times, and that's my standard deviation of the cross fit. These are supposed to match up. And this is what happens in the paradigm. But I was trying to show that plot. One of the histograms was plotting this with one of the summands. The other was just plotting the cross-fit estimate. And both were using root problems.
Sure, okay, I think I understand. What I was trying to get intuition for is why the covariance is negative between the different folds or whatever you call it here.
Right. So that is when we used MLEs for both the nuisances, and we thought that some universal phenomenon, and we thought that that should point to the fact that cross-fitting always helps, like you get even more variance reduction. But we have more simulations with other nuisance estimators now where we don't see negative anymore. We just see these are different. So we don't yet understand. We see that the covariances are non-zero, even on the Newton scale asymptotically, they survive. But I have to come back with an answer in like 2 months, like when they're negative and when they're positive. Because initially we thought we were actually like, there's something more going on with cross-fitting, and that it has further benefits in this regime. And you see that when you do things like MLE, which are unregularized, so you shouldn't actually be doing them. So cross-fitting kind of helps you with the variance eventually, which is nice. But then if you do like regularized things there, you start seeing like other things. So yeah, so I don't know if that is there. I mean, for the MLE it's there, but that's also I think because MLE is backwards. You kind of
All of
get
that
stuff
could have
back.
an analogy for cross-validation, right?
Oh yeah. So
And then the same question you could ask, exactly the same question for cross-validation.
Yeah.
And
Yeah.
then probably similar analysis as well.
I think so. So I started thinking about the cross-validation problem after we kind of were finishing this, and we were like, hey, this is like what you would expect in cross-validation also. And also like the upshot 3 was sort of a plot to see accept that. But yeah, that's all of this. I think the analysis should be similar. Yeah, I'll be happy to talk with you.
Okay, I think we should thank Pragya, and that concludes today.